So hello everyone, welcome to our channel. So today we're going to discuss about central processing unit. So we'll start central processing unit. So in that, if you see the topics, we have stack organization, we have instruction formats, we have addressing modes, we have reduced instruction set computer. Okay, so first we'll discuss about what stack organization is. So in stack organization, we have register stack, memory stack, and the reverse polish notation. Okay, so first what stack is. So we all know about what stack is. So stack is last in, first out. So whatever the item which we put in the last is the item which to be popped out at the first. Okay. So we are going to push the items into the stack, and if you want to take those items out of the stack, the last item which is put to be taken out first. So last in, first out. Okay. So we have register stack, memory stack, and reverse polish notations. Okay. So first, let us discuss about stack organization. So what stack organization is? So the CPU of most computers comprises of a stack. So, so central processing unit. So you know the importance of CPU. Okay. So without CPU, there is nothing. So the CPU of most computers comprises of a stack or a last in first out list. Okay. Wherein information is stored in such a manner that item stored last is supposed to be retrieved. So whatever be the item which is stored at the last is the first item which is to be retrieved. The operation of a stack can be compared to a stack of trays. Okay, so if you see one tray after other, so what will we do? The tray which is kept at the last is to be taken first. Okay, the last tray placed on the top of the stack is the first to be taken out. The stack in digital computer is essentially a memory unit with an address register that can count only after initial values loaded to it. So here, the stack in the digital computer. So what is the exact stack in digital computer? Is nothing but your memory unit. So everything is stored in memory, right? So with an address register. So here we have an address register, a memory register. So first, we essentially have a memory unit with an address register that can count only after initial value is loaded. Okay, so here we'll have a stack pointer. So what's the use of a stack pointer here? So stack pointer always points to the current item. Okay, is a register where the address for the stack is held because its value always points at the top item in the stack. So whatever be the top item present in the stack, this stack pointer points to that. The physical registers of a stack are always available for reading or writing, unlike a stack of trays. Okay, so here the physical registers of a stack are always available for reading or writing. So here stack contains two operations, insertion and deletion. So insertion is nothing but pushing items onto the stack. Deletion is nothing but popping out items from the stack. Okay, so a stack has only two operations, insertion and deletion of items. The operation insertion is called push, that is called push down, because it can be thought of as a result of the pushing a new item on the top. Okay, so for example, a stack will be empty. You're pushing the first item onto the stack. Now the first item, the top of the stack pointer points to the top of the stack. So we have only one item. So a second item is pushed onto the stack. So second item occupies the stack. Stack pointer will occupy the second item, third item, fourth item. So for example, we insert a 10th item. Now stack pointer will point to the 10th item. So stack pointer will always keeps on incrementing. So SP plus 1. So SP is stack pointer. So SP keeps on incrementing by 1. Okay. The deletion operation is called pop. So here we have insertion operation. At the same time, we have a deletion operation. So which is called as a pop, because it can be thought of as a result of removing one item so that stack pops up. Okay. In actual, nothing is actually pushed or popped in a computer stack. So we have a computer stack, so which is nothing but which we said is our memory unit. So nothing is pushed out, nothing is popped out. Okay. These operations similar to incrementing or decrementing the stack pointer register. So we have stack register, that is SPR. Okay. So next, now we'll see what register stack is. Okay. So there are two ways to place a stack. Either it can be placed in a portion of a large memory, or it can be organized as a collection of finite number of memory words or registers. So you can place in a stack either in a portion of a large memory. So we can directly put it in a large memory, or it can be organized as a collection of finite number of memory words. Okay. So the organization of a 64-word register stack is exhibited in figure. So 64-word register stack. So if you see the 64-word register stack, okay. So this is 64 word register stack. So here we have a program counter. Here we have a data register. Okay, here we have a stack pointer. So this is stack. So this is data. This is program. Okay, so these are all memory addresses, location. So 4001, 4000, 3999, 3998, 3000, 2000, 1000. So this is all memory unit. Okay, so here program counter always points to the current address of PC. So address register holds the address. Okay, the stack pointer, as we said, that every item is pushed onto the stack. Okay, so stack pointer holds the current top element of the stack. Okay, so here if you see the figure, it's nothing but computer memory with program, data, and stack segments. Okay, so here, three items are placed in the stack A, B, C in that order. Item C is on the top of the stack, so that content of SP is now 3. So like that, here the main thing is in a 64 word stack, the stack pointer contains 6 bits because 2 power 6 equal to 64. As we know that 2 power 6 equal to 64. So this stack pointer contains 6 bits. So since SP has only 6 bits, it cannot exceed a number greater than 63. So 64 in the sense will take from 0 to 63. So when 63 is incremented by 1, the result is 0. So if you see, this is 63 plus 1, we'll get 64. So the result is 0. But SP can accommodate only the 6 least significant. So how much does SP can accommodate? Stack pointer can accommodate only up to 6 least significant bits. Why? Because 2 power 6 equal to 64, which is nothing but from 0 to 63. Okay. So but when 0, 0, 0, 0 is decremented by 1, the result is 1, 1, 1. The 1 bit register full is set to 1 when the stack is full. And the 1 bit register empty is set to 1 when the stack of the empty of the items. Okay. So here DR is a data register. As we said in the diagram, DR is a data register which holds the binary data to return into or read out of the stack. So what is the main job of DR here? Data register, which is the data register that holds the binary data to be written or from the read out of the stack. So binary data, which is we can write into the stack or we can read out from the stack. So initially SP is clear to 0. So initially your stack point will always be set to 0. Empty is set to 1. So empty is set to 1 in the sense and full is clear to 0. Okay, so stack is empty and full is clear to 0. So that's SP points to the word at address 0. So which means that initially our stack is empty. And we have not written anything into the stack. We have not read from the stack. So we have not inserted anything into the stack. So the stack point will always points to the 0th location. So SP points to the word. So here we are calling it as a 64 word stack. Okay. So why 64? Why? Because 2 power 6 equal to 64, which holds the 6 bits. So SP points to the word at address 0 and the stack is marked empty or not full. If the stack is not full, that means if full equal to 0. That means when full will be 1, when full equal to 1, that means the stack is full. So we can't insert any more item. If full equal to 0, it means the stack is still stack contains some empty space so that we can insert. So if full equal to 0, a new item is inserted with the push operation. Okay. So this push operation takes 3 micro operations. See, SP plus 1. So when does this occur? SP plus 1. Why? Because if your stack is empty, you can if you have a space to insert items into the stack, then your stack point will increment to 1. Okay. So SP plus 1, and from memory address of that stack pointer we get from data register. So write item onto the top of the stack. Okay. So now top of the stack contains the item, which is current item. So check if stack is full. If SP equal to 0, that means if stack pointer equal to 0, that means nowhere you can insert the data. Then set the flag of full to 1. So remember, when full equal to 0, that means stack is empty, you can insert. When full equal to 1, then you can pop out. Okay. Next. The stack point is incremented so that it points to the address of the next higher word. The word from the DR is inserted to the top of the stack by the memory write operation. So here memory write operation is performed. So the storage of the first item is done at address 1, whereas the last item is stored at address 0. The SP reaches 0, that means the stack is full of items. So whenever stack is full of items, we can't insert any item anymore. Okay. So now we are going to clear the items. That means we are willing to delete the items. That means we need to perform the push operation. Okay. So if you see the push operation here, so if this is a push operation, read items from the top of the stack. So first we should read the top of the stack. Why? Because your stack is already full and your stack pointer points to the top of the stack. Okay, right. And your SP should get decremented to 1. Why? Your stack pointer is already full. Now your SP should get decremented to 1 so that we can pop out the item. So SP minus 1. So if SP double equal to 0, then full equal to 1. Check if stack is empty. Empty tends to 0. Mark the stack not full. The stack is not empty. Mark the stack not full. So in this way, we perform insert operation, that is push operation. We perform delete operation, which is pop. Okay, so this is all about register stack. So in our next class, we'll discuss about memory stack. Okay, so the students who are watching the channel for the first time, I request you to please subscribe my. So next is memory stack. So here previously we discussed about register stack. So next is memory stack. So stack can exist or can be executed in a random access memory attached to a CPU. The implementation of stack in the CPU is done by assigning a portion of memory. A portion of memory is assigned to a stack operation. The processor is used as a stack pointer to execute stack in the CPU. So what happens here? A portion of memory is assigned to a stack operation, and a processor register used as a stack pointer to execute stack in the CPU. So if you see the perfect example here, if you see this example, so if you see this is the memory unit and this is the address. Stack pointer always points to the 4001 address, 4001 address. Next, your stack pointer keeps on incrementing. Okay, so if you see here, displays the initial value of stack pointer at 4001 and growing of stack decreasing address. You can see the address is decreasing. Okay, so that's a basic importance of this memory register. Okay, so memory stack. Okay, so if you see the initial value of stack point is pointed at 4001. So generally what happens whenever we increments the stack point will, if stack point is pointed to 10th location, if stack pointer is incremented, it points to the 11th location, next 12th. Why? Because stack point is incremented to 1. So what exactly happens in memory stack here? Initially stack pointer will point at 4001 location. So it keeps on decrementing with the decreasing addresses. Thus, the first item stored in the stack is at address 4000. The second item is stored at address 3999, 3998, 3997, so on. So, if you see the insert operation, if you see the push operation, when compared with the register stack, the pop operation in register stack is exactly push operation in memory stack. Okay, why? Because your stack pointer is decrementing here. So, if you see the push operation here, SP minus 1. And M of SP, that is data register, is stored. The stack point is decremented so that it points to the address of the next word. A memory write operation insert the word from DR into the top of the stack. But if you take a pop operation, which is exactly push operation in register stack, okay, your stack point is incremented to 1. Okay, so if you see pop operation here, DR M of SP to DR. So here the write operation, here read operation, and SP plus 1. That the top item is read from the stack into data register. The stack pointer is then incremented to point at the next item in the stack. Okay, so the first case it is push operation, in the second case it is pop operation. Okay, so and the next is reverse polish notation. Okay, so reverse polish notation. So what is reverse polish notation here? So reverse polish notation is nothing but first we should know the infix and prefix. So infix is if we say A plus B. Okay, so plus will come first, next AB, postfix AB plus. Okay, prefix, a postfix, now infix. So reverse polish notation is a way of expressing arithmetic expression that avoid the use of brackets to define priority for evaluation of operators. So for example, 3 plus 5 into 7 minus 2, and the brackets tell us that we have to add 3 to 5, then subtract 2 from 7 and multiply the result together. In reverse polish notation, the numbers and operators are listed one after another, and an operator always acts as the most recent numbers in the list. Okay, so in this notation, the above expression would be 3, 5 plus. Okay, so we have 3 plus 5, so 3, 5 plus 7, 2 minus, and 3 plus 5, 7 minus 2, we have star in between. So star will come at the last. Okay, so 3, 5 plus 7, 2 minus and star. So reading from left to right. So this is interpreted as follows. So first we should push 3 onto the stack. So first we have 3 here. Next push 5 onto the stack. Okay. Now the stack contains 3 comma 5. Now we got plus operation. So takes the two numbers of the stack and then add together. So whenever plus is uncounted, so we should pop out 3 and 5 from the stack. Okay. So next to push 7 onto the stack. Next to push 2 onto the stack. Now stack contains 8, 7, 2. So what is 8 here? So we already added 3 and 5, right? So 3 plus 5 got 8, and we pushed on 7 and 2. Now 7, 2 again it's subtract. 7, 2 is subtracted, so we'll get 5. So now stack contains 8 comma 5. Now star is pushed onto the stack. Okay. Now star, one second. Now star is pushed onto the stack. So whenever star is pushed onto the stack, these two are multiplied, and finally we get 80. Okay. So this is called reverse Polish notation. Okay. So with this we completed our topic like stack operation, like register stack, memory stack, and reverse Polish notation. So in our next class we'll discuss about instruction formats. Okay. So please subscribe my channel, please support my channel all possible ways. Thank you very much, and have a